In this video, you will learn how to analyze a multi-story frame using cantilever method. Cantilever method is an approximate method of analysis of multi-story multi-bay frames. Using this method, we can analyze the multi-story frame subjected to horizontal forces only. There are various methods for approximate analysis of multi-story frames. We know that structures are subjected to gravity load, that is vertical loads, and horizontal load. Vertical loads are due to dead load and live load, or which is also called as imposed load, and horizontal load is due to wind load and earthquake forces. So to analyze the frame subjected to vertical loads or gravity loads, we have substitute frame method. And for the analysis of frames subjected to horizontal forces, we have three methods, that is portal method, cantilever method and factor method. So in this video, we are going to learn cantilever method for analysis of multi-story frames. First of all, we will understand assumptions made in cantilever method. There are 5 assumptions in cantilever method. First is, this method is applicable for the frames which are subjected to horizontal forces only. So load acting on the frame is horizontal. Since this method is applicable to the frames subjected to horizontal forces only, self-weight of the frame is neglected. Next assumption is, there is point of contrafacture at the center of each column. At the point of contrafacture, the bending moment is 0 and therefore we can consider the hinges at the center of each column. Then next assumption is, there is point of contrafacture at the center of each beam. So bending moment at center of each beam is 0. Therefore we can consider the hinge at the center of each beam. The last assumption is the most important assumption in cantilever method, that is, the intensity of axial stress in each column of the story is proportional to the horizontal distance of that column from the centroid of the cross-sectional area of all columns of the story under consideration. Since the stress equals to force upon area, then for the columns having equal cross-sectional areas, the force in column is also proportional to its distance from the centroid of the column areas. I will explain this assumption in detail. To understand the last assumption, let us consider this portal frame having area of column A1, A2, A3 and A4 as shown in the figure. Then consider the hinges at the center of each column as shown in the figure as per the assumption in cantilever method. Then separate the frame at the point of hinges and draw the free body diagram. After separating the frame at the point of hinges, we have to show the axial forces in column V1, V2, V3 and V4. We have to draw the CG line of the column, show the forces, tensile forces on left side of the CG line and compressive forces on right side of the CG line if the horizontal force acts towards right. If the horizontal force acts towards left, then show in reverse way. Let us assume x bar is the distance of CG line from first column. After that, show distances x1, x2, x3 and x4. These distances are distance of column from the CG line. For example, x1 is distance of first column from the CG line, x2 is distance of second column from the CG line, x3 is distance of third column and x4 is distance of fourth column from the CG line. So show all the distances and the axial forces in columns V1, V2, V3 and V4 on this diagram. I already mentioned that while drawing the axial forces in columns, that is V1, V2, V3, V4, for the columns which are to the left of the CG line, you have to show tension, and right columns, the columns which are to the right of the CG line, show the compression as shown in this figure. So after calculating the distances x1, x2, x3 and x4, finally we write that fifth assumption. So the last assumption states that the stress in first column divided by the distance of first column from CG line is equal to stress in second column divided by distance of second column from CG line and so on. Let us understand how to analyze a portal frame subjected to horizontal forces using cantilever method. Consider the multi-story frame as shown in the figure subjected to horizontal forces of 20 kN each at nodal point A and D. Let us understand step by step how to analyze this frame using cantilever method. Always start analyzing the frame from top story. So consider the top story. Assume the hinges at center of each column as shown in this figure. Then separate the story at the point of hinge like this. So we have to consider only 2 meter top part of top story. First of all, we have to locate CG line of column area for top story. Let us see how to draw this sketch. Consider leftmost column as reference. So draw a reference line at first column. Then draw a CG line and consider the distance as x bar. Then draw the axial forces in columns V1, V2 and V3. While drawing the axial forces, there will be tension in the column which are to the left of CG line, hence show downward arrows indicating tension in the column. There will be compression in column which are to the right side of CG line, hence show upward arrows indicating compression in the columns. Then write down the distances from CG line as x1, x2 and x3. In this example, the area of column is same. So let us assume the area as A. So there are 3 columns. So total area will be A plus A plus A is equal to 3A. Then we have to take the moment of all the column areas about reference axis. This is the reference line and we have to take moment of all the column areas about this reference line. So total area is 3A. So 3A into x bar is equal to moment of first column area, that is A into 0 because it distance is 0 from reference line. Then second column distance is 5 meter, so A into 5 plus third column distance is 5 plus 7, 12 meter, so it is A into 12. If we calculate this, you will get x bar is equal to 5.667 meter. That means the distance of CG line from reference line is x bar. Next step is to calculate the distance of each column from the reference line, that is x1, x2 and x3. Distance of first column from the reference line is x1 and x1 is nothing but x bar. So x1 is 5.667 meter. x2 is distance of second column from the reference line. So it will be x1 minus 5 meter. So it is 0.667 meter. x3 is distance of third column from reference line. So it is equal to 12 minus x1, which is 6.333 meter. Next step is, as per the assumption in cantilever method, we have to write this equation, that is stress in first column divided by distance of first column from reference line is equal to stress in second column divided by distance of second column from reference line is equal to stress in third column divided by distance of third column from reference line. Stress means force upon area. So stress in first column is V1 upon A1, stress in second column is V2 upon A2 and stress in third column is V3 upon A3. So we have to write this equation. We know the value of x1, x2 and x3. Area of each column is A. So we can cancel out A from all the sides and finally we will get the equation like this. Area of each column is same, therefore we can cancel A from this equation and finally equation will be V1 upon x1 is equal to V2 upon x2 is equal to V3 upon x3. So substitute the value of x1, x2 and x3 in this equation. We will get equation like this. V1 upon 5.667 is equal to V2 upon 0.667 is equal to V3 upon 6.33. So from this relation, we will get the relation between axial forces. So V2 is equal to 0.118 V1, V3 is equal to 1.117 V1. If you solve this, you will get these equations. After calculating the relation between the axial forces, we have to take the moment of all the forces about last hinge, that is moment of 20 kilonewton, V1, V2 and V3 about the last hinge. If you take the moment, you will get 20 into 2. So moment means force into perpendicular distance. So perpendicular distance of 20 kilonewton from the hinge is vertical 2 meter. So 20 into 2 minus V1 into 12 minus V2 into 7. And moment of last force, that is V3, is 0 because it is passing through that point. Then we know that V2 is equal to 0.118 V1. So we will substitute V2 as 0.118 V1. So there will be only one unknown in the equation, which is V1. So if you solve this, you will get V1 is equal to 3.12 kilonewton. And then using the relation, you can calculate V2 and V3 also. So this is how we can calculate the axial forces in columns of top story. So V1 is the axial force In leftmost column, that is 3.12 kilonewton, 0.37 kilonewton is the axial force in the middle column, and 3.49 kilonewton is the axial force in the rightmost column. We have calculated this using the relation V2 is equal to 0.118 V1 and V3 is equal to 1.117 V1. After calculating the axial forces in the column, you should always have the check, that is summation V is equal to 0. Total downward forces must be equal to total upward forces. So if you calculate V1 plus V2, you will get equal to V3. In same way, we have to derive the equation of axial forces for the bottom story. For that, we have to consider the hinges at the center of column of bottom story and then draw the sketch up to the center of column of bottom story up to hinges and show the forces and derive the equation. So we get similar equation because the position of CG line is same. So it will be V4 upon 5.667 is equal to V5 upon 0.667 is equal to V6 upon 6.33, which is very similar to earlier equation. So we get relation between the axial forces in the column. V5 is equal to 0.118 V4 and V6 is equal to 1.117 V4 as earlier. After that, we have to take the moment about the last hinge X. So for that, if you take the moment about X, the moment of top horizontal force 20 kilonewton is 20 into 7 because its distance from the hinge is 7 meter. Vertical distance is 7 meter. Moment of second 20 kilonewton is 20 into 3 minus V4 into 12 minus V5 into 7 is equal to 0. We know the relation between V5 and V4, so we can substitute V5 as 0.118 V4 and calculate the value of V4. So if you solve the equation, you will get V4 is equal to 15.59 kilonewton. So from this you can calculate V5 and V6. So from this finally we get the axial forces in column of bottom story. So V4 is 15.59 kilonewton. Then using the relation we can calculate V5 which is equal to 1.83 kilonewton and V6 is equal to 17.42 kilonewton. After calculating the axial forces in column, always have the check summation V equal to 0. So sum of downward forces must be equal to sum of upward forces. So you must get V4 plus V5 is equal to V6. After calculating axial forces in all the columns, the next step is calculation of shear forces in beams. So for that, we have to consider the frame and as per our assumption, consider the hinges at the center of each column, also at the center of each beam. Then separate the frame at the point of hinges in columns and beams. I will explain how to draw the free body diagram of this frame by separating it at the point of hinge. So the figure will look something like this. I will explain how to draw this figure First of all, draw the outline of the frame and break it at the center of each column and at the center of each beam. Then first of all, draw all the axial forces in top column which we have calculated, that is 3.12, 0.37 and 3.49. Direction also we have to draw as per the calculation, that is downward for column at A, downward at column at B and upward at column at C. Then equal and opposite. You have to show on the other part. So on the top it was downward 3.12 for the leftmost column. It will be upward 3.12 for the bottom part. After drawing the axial forces in top column, draw axial forces in bottom column, which we have calculated 15.59, 1.83 and 17.42. Then draw equal and opposite on the other part, like this. After showing the axial forces in top columns and bottom columns, we have to show shear forces in the beam. For that, you have to consider the leftmost corner, top corner of the frame, apply summation of vertical forces equal to 0. So, on the column, the force is downward 3.12. Therefore, on the beam, the force will be upward, which is also equal to 3.12. Once you show the upward force on one part of the beam as SAB, on other part of SAB you have to show equal and opposite. So it is downward as shown in the figure. So once you decide the direction of shear force on one beam, you have to show similar arrows for other beam, like SBC, that is shear force in beam BC, SDE, that is shear force in beam DE, and SEF, that is shear force in beam EF. So similar arrows you have to show and complete this free body diagram. And then consider each joint and apply summation of vertical forces equal to 0. Calculate the values of shear forces in the beam. So let us apply the equilibrium condition, summation of vertical forces equal to 0 at each joint. So we will start from first joint A and apply summation of vertical forces equal to 0. We will get shear force in beam AB is equal to 3.12 kilonewton. Similarly, if you apply summation of vertical forces equal to 0 at joint C, you will get shear force in beam BC is equal to 3.49 kilonewton. Applying equilibrium condition at joint D, we get shear force in beam DE is equal to 15.59, which is downward, minus 3.12. So it is equal to 12.47 kilonewton. In same way, we can calculate shear force in beam EF, which is equal to 13.93 kilonewton. This is how we calculate shear forces in the beam. Since our ultimate aim is to draw the bending moment diagram for this frame, we are interested in calculating the bending moments in beams and columns. So first of all, we will start with calculation of bending moment in beams. So bending moment in beam is nothing but shear force in beam multiplied by span of that beam divided by 2. So we will use this equation to calculate bending moment in beam. For example, bending moment in beam AB is equal to shear force SAB multiplied by span of AB, that is 5 meter, so 5 by 2. This is how we will calculate bending moment in all the beams. So bending moment in top beams MAB is equal to MBA, which is equal to 7.8 kilonewton meter, and MBC is equal to MCB is equal to 12.215 kilonewton meter. Similarly, we can calculate bending moment in bottom story beams. So for bottom story, MDE is equal to MED is equal to 31.175 kilonewton meter, and MEF is equal to MFE is equal to 48.755 kilonewton meter. So this is how we can calculate bending moment in all the beams. Next step is to calculate the bending moment in columns. So for calculating bending moment in columns, we have to apply the equation sum of column moments is equal to sum of beam moment at each joint. Let's see how we can apply this condition. So if you look at joint A, there is one column and one beam. Column is AD and beam is AB. So moment in column is equal to moment in beam. So MAD is equal to MAB, which is equal to 7.8 kilonewton meter. So MAD, that is the moment at the top of column, is also equal to moment at the bottom of the column MDA. Next, consider joint B. At joint B, there is one column BE and there are two beams BA and BC. Therefore, we can write moment in columns means MBE is equal to sum of moments in beams, that is MBA plus MBC. So we get moment in column BE is equal to 20.015 kilonewton meter. Then consider joint C. You will get MCF is equal to MCB is equal to 12.215 kilonewton meter. Next, go to joint D. At joint D, there are two columns DA and DG and one beam DE. So we can write the equation MDA plus MDG is equal to MDE. So we get MDG is equal to 23.375 kilonewton meter. In this, we have already calculated MDA from the top story and unknown is only MDG. And apply the same condition, that is sum of column moments is equal to sum of beam moment. You will get moment in column EH. Because moment in column EB is already known, so only unknown is moment in column EH, which is equal to 59.915 kilonewton meter. Then calculate moment in last column, that is MFI. MFC is already known, so only unknown is MFI. There are two columns and one beam, so you can calculate MFI, which is equal to 36.54. The most important step is to draw the bending moment diagram. In case of multi-bay multi-story frames, we always prefer to draw the bending moment diagram for column separately and bending moment diagram for beam separately. If the horizontal loads act towards right, we always get the shape of bending moment diagram for columns like this. You have to just draw this sketch and write down the ordinates. On the multi-story frame, if the horizontal loads act towards right, you will always get bending moment diagram for beams like this. You have to just draw this sketch and write down all the ordinates on this sketch to get bending moment diagram for beam. Some tips for analyzing any multi-story frames using cantilever method. Always start solving the frame from top story to bottom story. The sequence of calculation will be, first of all you have to calculate the axial forces in column using the assumption in cantilever method related to axial stresses in column. After that you have to draw the free body diagram of the frame and then calculate shear forces in beam using the joint equilibrium conditions. After calculating the shear forces in beam, you can calculate bending moment in beam using the equation bending moment in beam is equal to shear force in beam divided by half of the span of that particular beam. So after calculating bending moment in beams, finally you can calculate bending moment in columns using equilibrium condition. That is summation of moments in columns is equal to summation of moments in beam. After calculating all the bending moments, you can draw the bending moment diagram for this multi-story frame. I hope this video will be helpful to you. Happy learning!